I'll send you a link.
It seems that
the pointer is not working. Because I feel this way.
The pointer works, but the okay.
The mouse doesn't work.
Well, the page turn.
Great. Sure.
Okay. I think it's fine.
Okay. So, so you need to use this.
Okay. And thanks for coming. It's a great pleasure to see you here, and I will also appreciate my audience online, especially those who are in China. Yeah, it's pretty early in the morning in China right now. Okay, so yeah, so the title of my defense is large volume transfer for multi-axis. Oh, I think you changed this a little bit, right? Multi-axis and the string squeeze atom interferometry. Oh, did I open the wrong thing? No, this is the right
that's
thing.
Fine. That's fine.
Okay, yeah. Okay. Because the audience here is quite diverse, I would like to start with something that is not technical first. Otherwise, many people will have a very bad time. So I would like to first introduce a little bit about myself. Yeah, I'm from the city of Wuhan. Yes, exactly, the orange of COVID-19. Yeah, and this city is in central China, and the Yangtze River flows through it, and that is one reason why it is called the river city. But there are many cities on the Yangtze River. Why is this only this one called the river city? It actually results from this poem, Jadeful Sings in the Yellow Crane Tower, Plum Blossom Falls in the river city summer. I did this translation, and I wish it sounded like a poem. Okay, and I went to this university for my undergraduate study. The name of this university is also located in Wuhan, and the name is Huazhong University of Science and Technology. And Dr. Zifai Zhou is also from this university, and my predecessor, Ren Peng, is also from this university. But surprisingly, Professor Sharier does not seem to remember this university.
Well, to me, all the universities in China sound like the same. So
okay. Okay. Then I'll start talking about something semi-technical. That is my journey of publications. Yeah, these are my publications. These are my journal publications. I think I'd not to explain too much here. And these are my preprints on archive. And these are my conference publications. Okay, then I will start the technical part. But I will start from the very basic knowledge, and I wish everyone can at least pick up something here. So my project is on atom interferometry.
May I interrupt you for a second? I know that you have a very diverse audience.
Okay? Yes.
Your primary audience
yes.
Professor Kovachi and Professor Gerasi, okay? Keep that in mind.
Okay.
Don't go into too many details and things like that, okay?
Okay. Yes. So, let me just briefly start from the interference. So my project is on atom interferometry. Then what is interference? So what is shown here is just the water, nothing mysterious. And there are two oscillators creating water waves. And the water wave created by this oscillator, the left oscillator, interferes with the wave created by the right oscillator. And and the consequence of the interference is that at some point, at some positions, like positions along this line, the magnitude of the wave is increased. And the terminology is constructive interference. I think you can just sit wherever you want. And you can also go to get some food. And at some positions, like the positions along this line, the amplitude of the wave is suppressed, and the terminology is destructive interference. So interference is a very is a special phenomenon for waves, and we know that this is water. This is water wave, and we know that light is also wave.
I get a comment from people who are watching the on Zoom saying that we cannot see the writing on the slides.
Oh, okay. Oh, right. I forget to share the. I forget to share the. Sorry.
Your screen?
Yes. Well, this is the first time I do defense, but unfortunately, this is also the last time. So yeah. Hopefully. Who knows? Okay, who knows?
Should it be working now?
Yeah. Yes. Okay.
Hey, Sky, can you see it now? Guys, the word was completely.
Okay. Okay. Okay.
Go ahead, continue.
Yes.
Okay. Yeah. So, yeah, this is interference. Interference is a special phenomenon for waves, and we know that light is wave, so light can interfere. Oh, sorry. Yeah. But according to quantum mechanics, particles like atoms are also waves, and they're called matter wave. So atoms can also interfere, and that's where atom interferometry comes from. Okay. So of course, interference is a very interesting phenomenon, but is there any application? Does it have any application? The answer is yes. Interference can be used for making measurements. I think most of you have learned about optical interferometers, like the Young's double slit interferometer, like Michelson-Morley interferometer, and the Alexander.
Are missing there, right? Morley.
Okay, Morley interferometer and Alexander interferometer. So this interferometer can be used to measure the wavelengths of light. I think this is a high school homework problem for many of you. And Michelson-Morley interferometer might be the most famous one because over 100 years ago, Michelson-Morley used this interferometer to disprove the existence of ether. And maybe a few years ago, LIGO used a huge Michelson-Morley interferometer to detect the microwave gravitational waves. Yeah. And the Mach-Zehnder interferometer can be used to measure rotation rate. Okay. Similarly, atom interferometers are also sensors and that can be used for measurements. But they are inertial measurement sensors. So what is inertial measurement? Inertial measurement apparatus measures its own acceleration and rotation without any external references. Let me just give you one example. So if when you are sitting in a car with your eyes covered, you can still feel it if the car accelerates or decelerates or make a turn. And actually that is inertial measurement. But of course, we are sensors, but this sensor is quite insensitive. So we need more sensitive inertial measurement apparatus. And the atom interferometer is a good candidate for that. Okay, then let's go to the part of the atom interferometer. So atom interferometry is a method for inertial measurement, as I just discussed, and it has basically two general applications. The first is the practical application, namely the inertial navigation. So right now there are many technologies for inertial navigation, but generally they are not good enough because no one can drive only relying on inertial navigation. For this purpose, the size, weight, and the power of the apparatus is important, and these parameters are called swap. Yeah, and we proposed to use large moment transfer to improve the performance of the atom interferometry for inertial navigation, and that is my experimental project. And because for this purpose, the swap parameters are very important, we proposed a simpler way to implement large volume transfer, and we demonstrated, preliminarily demonstrated it in our experiment. And the second general application of atom interferometry is for fundamental scientific research, especially general relativity, because general relativity is about inertia and gravitation. Here, I just show two examples of the two examples of projects that based on general relativity that require precision inertial measurement. The first one is the geodetic effect and the dragging frame effect. The consequence of these two effects is that the orientation of a satellite changes a little bit after it orbits the Earth for one round. And this is a phenomenon predicted by general relativity, and yeah, it needs to be tested. And the other example is to test the equivalence principle. The equivalence principle states that the effect of acceleration is equivalent to the effect of let's continue. States that the effect of acceleration is equivalent to the effect of gravitation. Yeah, and the intuitive consequence is that a heavier ball falls at the same rate as a lighter ball. But the question is that, do they actually fall at exactly the same rate? Many theories predict that actually not. The falling rate differs by a little, and that's why it is still of interest to test the equivalence principle to a higher precision. I will not go to the details of these numbers, but the key point here is that if we incorporate large volume transfer and spin squeezing into atom interferometry, theoretically, the atom interferometry can reach sensitivity that is much higher than the current records achieved by the gravity probe B experiment and the microscope experiment. And these experiments are well, very expensive, and they take a long time to reach this sensitivity.
Gravity probe B was carried out for 50 PhD students and $100 million.
Okay.
Still, they got 80%.
Yes. Okay. So yeah. So that is why it's of interest to try to incorporate large volume transfer and spin squeezing into atom interferometry to enhance its sensitivity. Okay, the introduction has finished, and we finally enter the real technical part. Yeah. So I'll briefly review the conventional light pulse atom interferometer, and we only focus on the Raman transition based atom interferometers. Okay, in a Raman transition-based atom interferometer, the atoms are initially prepared in the lower ground state, and the temporal sequence of pi/2, pi/2 pulses are applied, and finally the population of the atoms in the higher ground state is measured, and that is the signal. This signal indicates the phase shifts accumulated in this interferometer. Both acceleration and both linear acceleration and rotation can induce a phase shift in this interferometer, and that is why an atom interferometer can be used for inertial measurement. Okay, now it's time to talk about large volume transfer. So, well, the phase shift accumulated in the conventional light pulse atom interferometer just depends on that the parameters like the half duration of the Raman pulse sequence, and if we do not want to make the experiment much longer, that generally we have no way to magnified phase shift. But large momentum transfer is a technique that is used to magnify the phase shift. Magnified phase shift. This is the first order large momentum transfer. So for the first order large momentum transfer, 4 additional pi pulses are added, and their effective propagation directions are anti-parallel to the original 3 pulses. And in this case, the momentum transfer is multiplied by a factor of 3. And we can also make the order of large momentum transfer higher by adding another 4 pi pulses. So in this way, another 4 pi pulses are added, and their effective propagation directions are parallel to the original 3 pulses. Even if you do not know what all these things are, you can still follow this pattern and predict for nth order of large momentum transfer what the pulse patterns should be. Okay, yeah. The existing method to implement large momentum transfer, we see the key technique we need is to change the effective direction of the pulses. Maybe I should still go back for this. Yeah. So we can see that to implement large momentum transfer, the essential technique we need is to reverse the effective direction of the Raman pulses. The existing method for that purpose is basically use the 2 Raman beams with orthogonal polarizations before polarizing beam splitter, and then the polarizations of the 2 beams are swapped, and in this way, the paths of these 2 beams are also swapped. So this method basically physically swap the propagation directions of the 2 Raman beams, and which also reverse the effective propagation direction of the Raman pulses. But this method has a few drawbacks. First, these 2 beams follow different trajectories. So in many of the interferometers, interferometers, basically the 2 Raman beams are first co-propagate, and then one or both Raman beams are reflected. People use that scheme because that scheme is makes use of fewer optical components, and it is also more friendly to alignment. So for this scheme, these 2 beams do not co-propagate. And they just counter-propagate. So it complicates the system. And the second drawback is that the 2 beams cannot be the 2 frequency components of the output of an EOM. Therefore, to produce such a pair of Raman beams, we either need to use 2 lasers with 1 laser phase locked to another laser. Or we can just use 1 frequency component in the EOM and another beam. And these 2 Raman beams cannot just be the 2 frequency components in the output of an EOM because they follow the same polarization and cannot be separated with PBS. And the third drawback is that there are only 2 options to swap the polarization of these 2 beams rapidly. The first method is that we just prepare 2 sets of Raman beams, and for first pulse, this set is used, and for a second pulse, the other set is used. But in this case, we obviously see that half of the optical power is wasted. But if we do not want to waste any optical power, the other option is to use the Poco cell, because Poco cell is just like is basically voltage controlled wave plate. So if no voltage is applied, it is ideally it is just a piece of glass. And if the voltage is applied, then it becomes a half wave plate and change the polarization of the beams. But a Poco cell also have some limitations. For example, ideally, when no voltage is applied, it should just behave like a piece of glass. But actually, that is not the case. Even without any voltage, it still distort the polarization a little bit. And also, because Poco cells are also UMs, namely electro-optical modulators, it has a limited, it can only withstand a limited optical power. And also, to drive optical Poco cell, high voltages required, voltages kilovolts. Therefore, it is of interest to to propose a new method for swapping the propagation directions of these two Raman beams, and this is our method. In our method, both Raman beams are retroreflected, so there exists two pairs of counterpropagating Raman beams, and also two pairs of co-propagating Raman beams. And if we scan the Raman spectrum of this configuration, we will see three resonant peaks. The two side wider peaks are produced by these two pairs of counterpropagating Raman beams, and the higher width is due to the Doppler broadening, and the central peak is produced by the two pairs of co-propagating Raman beams. Yeah. Therefore, we can see that by shifting from the left peak to the right peak, we effectively change from this pair of counterpropagating Raman beams to this pair. Yeah. Therefore, we do not need to physically swap the propagation directions of the two Raman beams, but just by changing the relative frequency between the two Raman beams to swap the directions of the Raman beams. Okay. Now that we have come up with an idea for large volume transfer, then we need to analyze the sensitivity, the sensitivity enhancement we can achieve with large volume transfer. It turns out that with a higher order of large volume transfer, definitely the phase shift is magnified, but due to the less than unity transition efficiencies of the pi pulses, the contrast of the interference fringes decreases as the order of large volume transfer increases. Therefore, there exists an optimal order of large volume transfer that maximizes the sensitivity, and we developed the method for that analysis. So this is just an example of the sensitivity versus the order of large volume transfer. We can see that with certain parameters, the sensitivity of the atomic interferometers with large volume transfer increases, but as the large volume transfer, but the order of large volume transfer keep increasing, the sensitivity actually decreases, and in this way we can find the optimal order of large volume transfer and the corresponding sensitivity enhancement factor. And of course, for different experiments or different models, we need to analyze the sensitivity accordingly. But this method, but this method provides this is a method of this is a fundamental method for such kind of analysis. So for the atomic interferometers I just discussed, there is a problem, namely the acceleration-induced phase shift cannot be easily distinguished from the rotation-induced phase shift. There are some methods to distinguish between these two types of phase shifts. For example, using several interferometers with atoms moving in different directions. But a simpler solution to that problem is the point source interferometer. So in a point source interferometer, the atomic cloud expands during the Raman pulse sequence, and in this way, atoms with different initial velocities follow different trajectories and accumulate different phase shifts. We can see here that the acceleration-induced phase shift does not depend on the initial velocity of the atoms, but the rotation-induced phase shift depends on the displacement of the atoms, which is determined by the initial velocities of the atoms. In this way, the atoms are ending at different positions actually gain different rotation-induced phase shift, but they all gain the same acceleration-induced phase shift. And therefore, if there is a rotation, the spatial distribution of the number of atoms in the detected state exhibits a fringe pattern, and the density of the fringes is proportional to the density of the fringes is described by this parameter, and this parameter is proportional to the angular velocity, which is the rotation we want to measure. And the phase and the acceleration-induced phase shift actually just introduce an extra phase to this fringe pattern, namely just globally shift these fringes. Therefore, a point source interferometer can measure both acceleration-induced phase shift and the rotation-induced phase shift, and it can distinguish between these two phase shifts.
Well, there is always the problem of 2 pi aliasing. Can you make a comment on that?
Of course, this is a fundamental issue for all atom interferometers, because what we measure is a quantum phase, a phase shift. Once the phase shift exceeds 2 pi, it is equivalent to a phase shift that is less than 2 pi. So basically that redundancy cannot be eliminated just with atom interferometers, but usually right now there are many proposals that the atom interferometers should be accompanied by classical sensors, inertial measurement sensors, so that the classical sensors can roughly tell us the acceleration and the rotation rate of the platform, and the atom interferometry is just used to further increase the sensitivity. Okay. So a key characteristic of the point source interferometer is that its signal is the spatial distribution of the number of atoms in the detected state, rather than the total population of the atoms in the detected state. In other words, the signal of the point source interferometer is actually an image rather than a number. Therefore, the sensitivity analysis for the conventional atom interferometers cannot be directly applied to the sensitivity analysis for the point source atom interferometer. And this is another work we have done. The basic idea is that for the conventional atom interferometer, the signal is just one number, and we can easily use the error propagation formula to propagate the uncertainty in the signal to the uncertainty in the measurements, like the acceleration or rotation. And in this case, the signal is just becomes a set of numbers, namely the number of the detected state atoms in each pixel, denoted as P1, P2, P3. Therefore, the measurements, these are not direct measurements, but they are proportional to the measurements, namely the rotation rate and the acceleration. They become a function of P1, P2, P3, and we can still use the error propagation error propagation formula to propagate the uncertainty in each parameter to the measurements. Yeah, the mathematics here is very complicated. So yeah, but I will just show the result. It turns out that if there are just a few fringes within the atomic cloud, the sensitivity depends on the acceleration-induced phase shift. But as the number of fringes within the atomic cloud increases, the sensitivity stabilizes to this value. Therefore, to get rid of the effect of the acceleration-induced phase shift, we should work at this regime. Yeah. Okay, that is the basic result. Now we come to the experimental part. Yeah. So we have built an interferometer with large volume transfer in our laboratory, and this is the pulse sequence.
So you didn't cite your paper in the previous slide. That's currently under review in Optics Express, right?
Yes.
Right.
Okay. Yes. Yeah, this is the pulse sequence we use to run the interferometer. We have the mod beam, which is 12 megahertz, ready tuned from this closed transition. I do not call it a cycling transition because Professor Sherrier always thinks that only the transitions between the two extreme Zeeman substates can be called cycling. So I just call it a closed transition. And the rear pump is resonant with this transition. The probe is resonant with this closed transition. And we have the Raman beams. The common detuning of these Raman beams is 0.9 gigahertz. And actually, this detuning is just from the f equal to 1 hyperfine state. Yeah. And the relative frequency between these two Raman beams is just the energy gap between the two hyperfine ground states. So the first step in the atoms is to in the experiment is to capture the atoms in a magneto-optical trap. So we have the mod beams, we have the magnetic quadrupole on, and we have the repump. And when after the atoms are captured in the magneto-optical trap, then we implement the polarization gradient cooling, and which is also sometimes called hemolysis cooling. And that stage is implemented by first turning off the coils for the magnetic quadrupole, and then ramp down the frequency of the mod beam by another 40 megahertz. With the repump on. So when ramping down the frequency of the mod beam, the intensity of the Raman beam is also ramped down. So in that way, we implement the polarization gradient cooling and cool the atoms to a temperature of like 10 or 20 microkelvins. This is not quite good, and I'm still working on improving the cooling process. And after this step, then we go into the step of implement the Raman beams to induce the interference. So first we turn on the bias coils to apply a biased magnetic field, and then the Raman pulses are applied. After the Raman pulses are applied, the biased magnetic field is turned off, and then we apply the probe beam to measure the number of atoms in the detected state, and that is our signal, which indicates the phase shifts of the interferometer. And this is our optical system. Let me take a look at the time. Okay. This is our optical system. So we use these three lasers we use one external cavity diode laser. This laser has the highest power. It has an output power of 1 watt, and we have 2 dBr lasers. Well, I do not want to go to the details of the optical system. I just want to explain how we produce the moth beam. So the moth beam is produced by guiding a piece of output from the external cavity diode laser through an AOM in a double pass, in a Cas I double pass configuration. And during the polarization gradient cooling, the modulation frequency of this AOM is ramped down from 40 megahertz to 20 megahertz. In this way, first, the frequency of this beam is ramped down, and second, because the AOM does not have a wide bandwidth, when the modulation frequency changes, the intensity actually is also the diffraction efficiency also decreases, so that the light intensity is also decreased. Okay, and the rest of this optical system are just using AOMs to shift the frequencies to the desired values. Okay, this is the actual. This is how my experimental systems actually look. This is the vacuum glass cell where the atoms are, and we have all the fiber output ports and magnetic coils. These two photos show the optical system from 2 different perspectives, and this photo shows the electronic system. The electronic systems are basically the drivers for the AOMs and the EOM, and this device is a national instrument device used to producing the pulses and acquiring data and taking data. These are the experimental results we have obtained. So we have tested this system with different configurations of the Raman beams. So in the beginning, we just tested the system with a pair of co-propagating Raman beams, and we have obtained this Raman spectrum. These are just all the transitions between all the Zeeman substates for Ruby-85, and this is.
So that's taken in the presence of some biased magnetic field, right?
No. With no
ambient magnetic field.
Yeah, ambient magnetic field.
But I mean, what I mean is that if there's no magnetic field, all those lines should be degenerate, right?
Yes, exactly. Yeah, and this is a Ramsey fringe pattern. And later we tested the scheme where only one Raman beam is retroreflected. So in the Raman spectrum, we have 2 peaks, one wide peak and one narrow peak. The narrow peak is produced by this pair of co-propagating Raman beams, and the wide peak is produced by this pair of counter-propagating Raman beams. Again, the higher width is produced is due to the.
So I'm going to slow you because since nobody else is asking me any question.
Yes.
I'm going to have to jump in. I know you are talking about a lot of stuff.
Yes.
Some of you went very quickly, but this is a key point of your work, so I'm going to ask you this question. So,
okay,
why is there a difference in the Doppler width for the co-propagating case and the counter-propagating case? Just give us a simple explanation.
Well, the simple answer is this question can be explained by the effective wave number of the Raman pulses. But if I want to discuss further, I need to explain what the effective wave numbers are. But briefly speaking, for the counter-propagating Raman beams,
you don't need to talk about effective wave number. It's just you're producing a 2-photon transition, right?
Yes.
So in one
Oh,
case.
okay, I understand what you want me to say. Yeah. So for the counter-propagating co-propagating Raman beams, the sign the sign of the Doppler shifts for each beam is are the same. So the Doppler shifts generally cancel each other, or cancel each other.
Does it exactly cancel or just
No. Because the wave numbers of these two beams are not exactly the same. These beams differ by, for example, for Rubin 85, which is the atoms I'm using. This difference is about 3.0 gigahertz. So yes, so the wave numbers also differ by a little, but but that is on the in the microwave regime, and the Doppler shift for microwave is very small.
Well, so for example, if you use room temperature atoms,
Yes.
the co-propagating Doppler width is about for rubidium 85.
Yes.
About 5 kilohertz.
Okay.
In case you didn't know that number.
Yes.
That's for room temperature atoms. Okay,
Yeah.
continue.
Yes. Yeah. And I have not explained the counter-propagating case. For the counter-propagating case, the sign of the Doppler shifts for the two beams are opposite, so they just add to each other. Yeah. Okay. So in this case, we have narrow peak and wide peak. Again, the wide peak is produced by this counter-propagating Raman beams. And these are the interference fringes as a function of the half duration of the Raman sequence. This plot shows the case where there is no effective acceleration, meaning that we just held the we just hold the relative frequency between the Raman beams constant. And in this case, we chirp the relative frequency between the two Raman beams to simulate an effective acceleration. So in this case, the effective acceleration is only a fifth of the gravitational acceleration. And that is the interference signals as a function of the.
So that is essentially your demonstration of accelerometry with atomic interferometry.
Yes. Yes.
Can I just ask you a technical question? How experimentally are you implementing the situation where you retroreflect only one of the two Raman components? Is that using polarization?
Oh, yes. Yeah. So my research journey is very long, and I changed the configurations several times. And what I just showed you was just the latest configuration, the latest experimental system. Yeah. So in my research journey, I did implemented a scheme where that these two Raman beams have orthogonal polarizations.
So in what you're doing in that diagram, they have orthogonal polarizations, and then only one of those two polarizations is retroreflected. Is that using like because you have a PBS or something on the retroreflection path?
Yeah, exactly. Yeah. And that scheme was I learned that scheme from the NIST PSI paper, and in their design, they just retroreflected one beam.
Okay.
And finally, we tested the case where both Raman beams are retroreflected. So in the Raman spectrum, we have 3 peaks, as I just discussed, and we have got some preliminary results for the large volume transfer. I will discuss a little more about this signal and explain what it is. Yeah. So we tested the simplest version of the large volume transfer, namely the first order large volume transfer. It turns out that due to the relatively low transition efficiency of the pi pulses, all these 3 trajectories exist. So ideally, we should only have trajectory 1 and trajectory 4, but actually, trajectory 2 and there are some atoms following trajectory 2 and trajectory 3. Yeah, to eliminate the effect of the 3 original random positives, when we test the large volume transfer, we hold T constant while scanning T naught. Yeah, and the theoretical signal should looks like looks like this. So there is a baseline, and there are 2 sinusoidal sinusoidal signals due to the, and this is the this signal comes from the interference between trajectory 1 and trajectory 4, which is the designed one. And this sinusoidal signal comes from the interference between trajectory 1 and trajectory 3, as well as between trajectory 2 and trajectory 4. So the ultimate signal should be in this form, and this signal matches this form. So we believe that this is evidence for the existence of large moment transfer. Yeah.
We'll have to see if the applied physics cluster reviewers buy that, but I buy that. So hopefully we can get better results soon. But
yes, and right now I'm still working on improving the interference signal. Yeah.
If I could just ask a question about the path diagram before we go on, are there also paths like if say for pulse B minus 1, if that pulse isn't perfect, so there's some atoms, or I guess you're showing that one not affecting trajectory 2. What would it? Yeah, maybe I'm misinterpreting. Would this pulse would it, because the A1, I guess it couples this dashed line and it couples this in this state. Would we expect that this state be branched off by state B minus 1, but there's just some that you're not showing for clarity on the diagram?
Exactly. So because these random pulses are not perfect, at the application of each pulse, definitely there are some. There are 2 trajectories following each pulse. Yeah, but I'm only showing the trajectories that finally will have an effect in the signal.
So you're showing the ones that actually will sort of overlap at the end, not the ones will just be
exactly.
So for the kind of detection he's doing right now, which is just a population of one state, might be okay. But for a point source interferometer, of course, it's going to have a major distribution problem. So to extend this to the actual point source interferometer case, we need to improve the signal quality more. But it is okay. All right, continue.
Let me take a look at the time.
And do you have a question?
Sorry, just on this note of the different paths and the multi-path interference effects. So you mentioned the interference between path 1 and 4, and you said also between 1 and 3 and 2 and 1. But it seems like 2 and 3 also come together unless I'm missing something, and does that give you a different momentum?
Exactly. That is why I hold T constant and only scan T naught, because 2 and 3 are actually the conventional atom interferometer without spin squeezing. So if I do not change the value of T, they should not.
I see. It's like some constant. Okay.
Yeah. And that's exactly the reason why I just scan T naught. Otherwise, it is just messy. During the spec test, I showed you a signal for large movement transfer, and in that case, I scanned T, and that signal was just very messy, and we did not know whether large movement transfer actually happened.
And just sorry, one last thing, just to make sure I'm appreciating the take-home point, which I think I do, but I just want to check. It's that in this method by sending the two beams down together, you can just do a frequency shift between those two beams and effectively get a K reversal without actually having to use a Pockle cell to physically flip the direction.
Exactly.
Yeah. Okay.
Well, so the story is a little more complicated. So, I mean, he can tell you, but I'll tell you quicker. There's one technique we proposed, which is in the paper that's done in review, where we give the atoms a constant push.
Right.
So there's a constant Doppler shift, right? But the experiment that we're doing here is we are at the mercy of gravity. So the velocity is actually continuously changing, and you're going to different pulses. So the way we avoid the problem for that is the Doppler shift has to be large enough so that the three peaks that we are showing, they are clearly separated.
Resolved. Right.
So as long as they're separate, it doesn't matter if the separation increases.
Yes.
We can still
you can still do it.
One or the other.
As long as those different peaks are resolved and not talking to each other.
So as long as the initial velocity due to the drop is large enough to separate the peaks, then that gives us the ability to just focus on that.
Yeah.
And then any additional acceleration that we see after that is the actual acceleration we're measuring. Yeah. So that is the way where. But eventually we want to either do it in a horizontal experiment or go to space and do a constant velocity experiment.
Which is then there where you would want to do that, do the launch.
Yeah, go ahead.
Okay, this is just some challenges I have encountered in my experiment. And right now, actually, I'm still working on some challenges. Yeah.
Also, one of the key things that he's doing, he didn't mention, is that most of the best and successful point source interferometers are done with 87 rubidium, for various factors. So we had to change the mid-course and now move to 87 rubidium, which is a whole bunch of changes in the system. But fortunately, he promises to stay around as a postdoc, so we'll get through that. We'll hold up his salary every month. When you're a graduate student, you have a hold, right? Yeah. When you're a postdoc, you can walk out next day. So we just withhold the salary for a couple of months.
Organize a postdoc union. Well, you can hold it, but you can just you cannot eliminate it. That after 3 months, you need to pay me the salary for 3 months. Okay, now we go to the spin squeezing, and we only focus on one axis twist squeezing. Originally spin squeezing.
So I should give you a warning. We're at 6:30 now, 6:32.
Yes.
So you need to wrap it up in 15 minutes. Okay.
Okay.
Try to do that. Okay.
Okay. So originally spin squeezing is used to suppress the quantum noise. But that is only significant only if the quantum noise is dominant. Later, it is realized that spin squeezing can be used to magnify the phase shift, which is always significant. And the way to magnify the phase shift with spin squeezing is to use the so-called echo squeezing protocol. In 2016, the conventional echo squeezing protocol was proposed, and last year we proposed the generalized echo squeezing protocol. And the generalized echo squeezing protocol has several advantages compared to the conventional echo squeezing protocol. We'll first take briefly review one axis space squeezing. This is the Hamiltonian for one axis space squeezing.
I should just mention that these research are done completely in parallel, independently. It's not like we saw the echo squeezing protocol and then decided to generalize it. We found our results in a completely different way, and later on we realized the similarity between them.
Yes, exactly.
Right. Okay. Continue.
Yes, and right now I will not explain what SC is. SC.
Continue.
Yes. And this is the corresponding propagator for one-axis twist squeezing. Practically, one-axis twist squeezing. So in our design, one-axis twist squeezing is implemented by cavity. Yes.
Obviously, rushing doesn't mean skipping. You have to still say at least the important point. You have to at least say what S sub Z is and all that stuff.
Okay.
You cannot just, otherwise it will be like showing pictures and okay.
Okay.
So at least say, but just say it to them.
Yeah. Okay. Well, to explain it, it is a long story. I will try to make it short. So every two-level system is mathematically equivalent to a spin-half spinner. Therefore, we can always use the language of spin to describe systems of two-level systems. And this SC is just the collective SC spin operator. Yeah. Okay. Yeah, and this is the corresponding propagator. In our design, one-axis or spin squeezing is implemented just by cavity-mediated nonlinear interactions between the atoms. These two videos show the Huseman-Quisling probability of the quantum state as a function of the degree of squeezing. And with these videos, we can intuitively see the effect of spin squeezing. First, I will show the even.
Junior, may I interrupt for a second?
Yes.
Obviously, you're going to show a lot of very complicated stuff later on, okay?
Yes.
So at least to make people happy,
yes,
to spend a little time here to show the basics. So what you are showing there on that sphere, what is that circle? Is there some kind of uncertainty? What uncertainty does it represent? This is the basic story of spin squeezing.
Okay.
If you don't say that, then nothing is going to get across.
Okay. So, well, okay. So this sphere, this sphere actually represents the quantum noise in the along the y direction and along the z direction, and there is actually no uncertainty in the x direction. I cannot explain the meaning of xy here.
Let me try.
Okay.
So all of you know that if you have a electron spin half, and if you put it in eigenstate of, let's say, x, then the sy and hj components remain uncertain, right? So that gives you an uncertainty in your momentum. Now, if you have n of them, those uncertainties just add by the sum of the squares, square root of the sum of the squares. So that sphere just essentially represents the uncertainty in the SZ and SY for a large number of spins. And when you are doing interferometry, like a clock or atom interferometry with the system, that is the uncertainty that effectively limits your sensitivity. So the goal of spin squeezing is to reduce the uncertainty either by squashing along one axis, or a more esoteric situation happens when you split that into Schrodinger cat state, where you get the most reduction, which is technically not squeezing, but it is the ultimate of what can be achieved by using this process. That's the summary story. Now continue.
Oh, okay. Even I cannot understand.
Stefan did. I saw him smiling.
Okay. Yeah, let's watch the video. Yeah. Squeezing. Yeah, squashed. Okay, and ultimately, a state consisting of two coherent spin states are formed. We can see one circle on this side of X and another circle on the other side of the X on the X-axis, and this is called an X-directed Schrodinger cat state. And for the odd n case, we range the number of atoms. We can see something similar. Okay, also, finally, a Schrodinger cat state is formed, but this is a y-directed Schrodinger cat state, and that's why we need to distinguish between the even n case and the odd n case. That's a very special characteristic of one-axis twisted squeezing. Okay, and these are the protocols. These are the two versions of the generalized echo squeezing protocols we proposed, and this is the conventional echo squeezing protocols. I need to mention here that the actual protocols for the atomic clocks are very complicated, and the actual protocols for the atom interferometers are even more complicated. But mathematically, they are equivalent to these simple three-step protocols. And this simplification is very important for theoretical analysis. And it is this simplification that helped us see why our protocols are actually very similar to the conventional echo squeezing protocols. And that is why we just call
similar but better.
Better. Yes. Okay, and next I will show why they are better. These are the sensitivities of these three protocols. The first two columns are the generalized echo squeezing protocols, and the last one is the conventional echo squeezing protocol. And the blue curve shows the sensitivity. And we can see that for the conventional echo squeezing protocol, the sensitivity first goes up and then decreases to 0.
Well, you have not defined even what those lines are, So take one of those graphs, explain what the solid dotted dashed line represents and the solid line represents. So the dashed line is the standard quantum limit, things like that.
Let's first just focus on the blue solid line.
Okay.
The blue solid lines just are the sensitivities. The sensitivities. So let's first take a look at the sensitivity of the conventional echo squeezing protocol. We can see that the sensitivity first goes up, but then it just quickly drops to 0. Yeah. But for the generalized echo squeezing protocols, we can see that the sensitivity increases to a level and remains almost constant for a wide range. The x-axis is just the degree of squeezing. Yeah, and this is an obvious advantage of the generalized echo squeezing protocol. The green dashed curves are Kramerov bounds, which are the theoretical maximum achievable sensitivities, and we can see that for the generalized echo squeezing protocols, the actual sensitivity is very close to the theoretical limit. But for the
may I ask you a question?
Yes.
So of course your notations are very obscure. I know what they mean.
Yes.
So just put it in perspective. Let's say I have a million atoms,
okay,
and I'm doing to experiment for a given measurement time.
Okay.
So if I go from the dashed line to the line that says 1, okay? How much better my clock is going to be?
1000.
Right. So you have to make sense of that. Otherwise, people don't know what the hell you are showing. Is it like 0.8 improvement? Then nobody's going to buy anything that has a 0.8 improvement. Okay. So that is the Heisenberg limit, which is it gives you a square root of n. And then if you can get it, you'll be very rich because you are improving the sensitivity of devices by a factor of 1,000. Okay.
Yeah.
So, but there's a promise to get there.
Yeah. But the prerequisite is that we use 1 million atoms. But right now the record is only 100 atoms, right?
No, 10 to the 5.
Oh, okay.
The squeezing experiment at Stanford was done with 10 to the 5.
Okay.
The improvement was factor of 10. That's what he's talking about. Yeah, factor of 100 is a 10 dB squeeze.
Okay.
The actual improvement was a factor of 10.
Oh, yeah. But they're actually not using echo protocols. They're just...
No, that's right. But that was the best that has been achieved. Yes.
Okay. And this is the effect of spin squeezing from another perspective, which are the interference fringes, which is the narrowing of the interference fringes. So in each plot, the plotting ranges from -2 pi to pi. This means that if we do not use spin squeezing, there is only just one fringe there. But with spin squeezing, we can see that the interference fringes are significantly narrowed. And we can see that the generalized echo squeezing protocol can narrow the fringes further than the conventional echo squeezing protocol. And that is, from another perspective, why this protocol has some advantage.
So in the limit where you get to the Schrodinger cat state,
Yes.
by what factor do the fringes get narrowed?
Narrowed compared to what?
To the unsqueezed fringe.
And
you have to mention these things, right? So people get
yes.
a sense of that, right?
Okay, yeah, and actually these two diagram plots show the case of Schrodinger cat states. Yeah, the fringes are magnified by a factor of n compared to the case.
So it sounds like science fiction, right? So you may get a clot that has a kilohertz Ramsey fringe, and then you get to that state, it would become a millihertz Ramsey fringe, okay? And I told the DARPA program manager, he says, I'll never believe it until I see it, okay? So it is really hard to believe that this can be achieved, but it is true. It's just a difficult thing to do. Continue.
Okay, and this is just a more detailed explanation of the effect of spin squeezing. I will not go to the details here. This is the sensitivity which I just showed, and this is the phase magnification factor which describes the narrowing of the fringes, and the quantum noise amplification. This is just another aspect. But this is not a very.
You're skipping the important part. You know, if you're going to give a talk, you have to point out the important point. So the critically important point here, right? So you're saying that you are magnifying the fringes by a factor of n, right?
Yes.
That doesn't sound right because the Heisenberg limit only says that you should be able to improve it by a square root of n. So what is going on there, and how is that useful?
What is going on there? Well, because as the fringes get narrower and narrower, the quantum noise level is also increased. Therefore, we do not break the Heisenberg limit. But if the fringes are significantly narrowed and accompanied with the increase in the quantum noise level, detection noise becomes not important, because compared to the quantum noise, that is detection noise level becomes low. Yeah. Okay, this is the explicit echo squeezing protocols for the atom interferometer. So for the atom interferometer, a key problem we need to solve here is that for the conventional atom interferometer, the first pi/2 pulse actually serves two purposes. The first purpose is preparing the inertial internal state of the atoms, and the second purpose is to impart momentum to the atoms. But for the for spin squeezing, these two processes must be separated, because for the spin squeezing, the state preparation process is fairly complicated. So we need to first prepare the internal state of the atoms and then impart momentum to the atoms to start the interference. And we can also incorporate both large moment transfer and spin squeezing into an atom interferometer. And these are the explicit protocols we have proposed. Okay. I'm about to reach the end. And we
also go back to that slide. You are just cutting yourself too short. So you talked about how you're going to do your system to test of the equivalence principle. So mention that this is designed for that, right? So this is the proposal where you should not, how to do this with two species of atoms.
Yes.
And then augmented by large momentum transfer and spin squeezing.
Yes.
And you estimate that you should be able to measure the Atomos parameter to what value? You claim that it's going to be much better than the microscope in your beginning of your talk, right?
All right.
So here is your chance to tell people us, right?
Okay.
You expect it to be able to achieve.
Well, of course, that all depends on how what order of large moment transfer you can implement, and also to what degree we can use spin squeezing. And actually, I forget all my estimations.
Okay, what's 10 to the minus 20 is a rough estimate.
Oh, okay. Oh, yeah. We adjust the parameters to make up this number, right?
No, I mean, we consider parameters and then we go to space.
Yes.
And we run this experiment for 160 days.
Yes.
You cannot be wishy-washy like that. Then nobody will ever accept your papers, You have to say, this is what we claim, and Tim is a co-author on this paper,
yes.
and this is the justification. You cannot simply hand wave and say, well, we kind of do this, we kind of do that, okay?
Okay.
So this was based on systematic estimate of what can be achieved, right?
Right.
Right. Otherwise, you can, as if 10 to the minus 30 if you're just dreaming. So you have to point out what's the practically potentially possible, right?
Right. Yeah. Yeah. But we just assumed that we just implement momentum transfer with an order of 10. Yeah. Something like that. But yes, we can go to 20. But yeah. We just use the parameters that may sound practical. Okay, and we're also working on experiments, experiments of spin squeezing. So of course our target is to incorporate spin squeezing to atom interferometry, but because atom interferometer is much more complicated than atomic clocks, so our first target is to
that's not the right perspective. We want to do both. It's just this one is initially easier than this. We're not doing. We want to do both clock and interferometer.
Yes.
So we're doing the clock first because it's relatively easier.
Yes. Okay. Because this is relatively easier, we will. We plan to do the atomic clock first. So we proposed this spin squeeze CPT clock. Well, yeah. It is almost 7, so.
All right. Well, but let me just finish in 30 seconds. You should have added some more in detail in there. So a CPT clock is just like a microwave clock.
Yes.
Except that it's done with 2 laser frequencies, which produces the microwave excitation. And this protocol can be applied to microwave clock too, but in some ways the CPT process is more easily compatible with the apparatus. And so idea is that you apply the squeezing protocol to essentially a microwave clock, except that it is in the form of a 2-photon clock.
Okay.
Right? That's the idea.
Okay.
Okay. All right. Continue.
Yeah, and then I will just show what has already. This is our experimental design for the spin squeeze CPT clock, and this is what has already been built in our laboratory by my coworkers. But I will work on this later when I become a postdoctoral researcher. Yeah. And finally, acknowledgements. So first, I would like to thank my advisor, Professor Salim Shahriar. Do you want to wave to the audience? Okay. And my committee member, Professor Timothy Kobachi. Do you want to wave to the audience? And also the audience. Okay.
Father is watching. So
And Professor Andrew Geraci. Okay, thanks. And these are the co-authors of my papers. And I would also like to thank my group members who are not shown on my on my papers. Yeah, like Olian and Roshi, and Stefan, who have also helped me a lot. And I would also like to thank my family and friends who have provided me with great help, with great support, so that I can finish my PhD journey. And thanks to you all for coming, either in person and virtually. Thanks.
But Tim and normally there is 2 stages. We do the questions by the committee and then the questions by the Do you want to do it that way or just? So, you guys have any questions? I was going to, yes, go ahead.
It's about like CPT as in like charge parity time limit, or what is the CPT there?
CPT stands for coherent population tracking. And actually, it is related to the phenomenon of EIT, electromagnetic induced transparency. It just means that when you apply two beams with the relative frequency equal to a certain value, there is a dark state, and all the atoms are just pumped to that dark state. That is why it is called population trapping. And the coherent just refers to that the state consists of a pair of coherent states. Okay.
Well, so that's the important part. So normally when an optical pumping process happens, it's an incoherent process. But during this process, the state that the system pumps into actually has a coherence between them. Thus, for example, you'll have a microwave, a magnetic moment, for example, non-zero. So that's why it's called coherent population trapping. And it's actually exactly equivalent to the state that you can generate when you put all the atoms in one state and apply a microwave pi/2 pulse. That creates a coherence between the two states, right? So the CPT process produces the same state, but through optical pumping process. And that's why it can also be used to make a clock, just like a microwave clock.
Yeah, I think you demonstrated spin squeezing over 100 atoms. And, what would be the biggest challenges in decreasing that number?
Oh, actually, we have not demonstrated that.
So
Yeah.
that's theoretical.
Yes. Well, that work was done by Stanford.
So what was your question? I didn't clearly understand your question.
Yeah, so by demonstrating the building the spin squeezing state over 100 atoms would be the main experimental challenge.
100 atoms. I don't know where you got the number 100 atoms from. What we were talking about is not 100 atoms. What we were saying was that there was a factor of 100 suppression in the quantum noise for 10 to the 5 atoms. So the factor of 100 is a suppression of the variance. So the actual improvement factor was actually a factor of 10. So if you do it with 100 atom, it wouldn't be. The problem is that this is a problem that exists in the optical world. Because you make a device, its sensitivity is better if you have more atoms, right? So if you give, and typically you can make these clocks and interferometers with say 1 million atoms. And if you have to give up a lot of those numbers just to implement squeezing, that doesn't help. And that is one of the problems with the spin squeezing demonstrated with Bose condensates. They only spin squeeze like 300 atoms. And you compare that with an unsqueezed clock that has 1 million atoms, the unsqueezed clock is better. Same thing in optics. You make an interferometer, you just put a lot of power in it, it becomes much better than the squeeze interferometer. The only exception is LIGO, because LIGO is already at the limit of the most power you could put in that device. And so therefore, even adding a little bit of squeezing is still better. So in the case of the atomic world, what you really want to do is stick to the number of atoms that you normally use and then produce this curved enhancement, which is the holy grail. So remember, this is going to be a 10-year-long postdoc.
If you can offer me a professor position at Northwestern University, I can.
Well, that comes after 10 years.
Yeah, if that happens.
Okay, you have another question?
Yeah, so I still want to sort of kind of clarify my understanding. So in the first part, you sort of talk about like rotation and acceleration sensing with like a large momentum transfer and point source interferometer. So for the second part, like I guess like that part of work is not directly related to the second part, like the spin squeezing and some like echo of the protocol that you were talking about. So like so to make the logic clear, what's the general motivation for the the second part of work, or is it also for a methodology to improve the sensitivity, or is it something related to the first part?
Oh, yeah. So both large volume transfer and spin squeezing are techniques for increasing the sensitivity of an atom interferometer. So yeah. So basically, spin squeezing can also be used for atom interferometry to enhance the sensitivity. But of course, the point source interferometer is a little bit confusing because spin squeezing, so far, we believe that spin squeezing cannot be applied to that. But generally speaking, an atom interferometry can be used to measure acceleration and rotation, and large moment transfer and spin squeezing can be used to enhance the sensitivity. That is the logic. Yeah.
So, do you want to comment on why it would be difficult to apply spin squeezing to point source interferometer?
Because the essence of spin squeezing is actually to generate entanglement. So meaning that ultimately the atoms are entangled. But for point source interferometer, atoms with different initial velocities actually gain different phase shifts. So there is no point to entangle them. Yeah. So this technique can be applied to point source interferometer only if we can entangle the atoms with certain initial velocities. Yeah.
So basically, what you're saying is that in the point source interferometer, there are many interferometers
yes.
for different velocity groups. Right?
Yes.
So if you want to apply the spin squeezing technique to enhance the sensitivity of that, you need to somehow spin squeeze each of those groups separately.
Yes.
That's not impossible. It's just we don't know how to do that yet, right?
Right.
So that is what has to be done. It's just for now we are focusing on the simple atom interferometer that starts with just one group of very cold atoms and not in the point source configuration.
Right.
But that is the idea. When Greg comes back, that's what I'm going to ask him to try to figure out.
Okay.
We'll have to do that for each velocity group separately.
Okay.
Any other questions?
More questions? And also, audience, virtual audience. Any questions?
May I ask a question online?
Yes, please.
Okay. So, my question is about the GPT clock.
The CPT.
One of my research areas is the microwave remote sensing of the atmosphere, used for improving weather forecast. And we use the crystal clock in the microwave receiver. The atomic clock has advanced in long-term stability over the crystal clock. So I see the experiment system picture. It seems complicated and not. Is it possible to make the CPT clock a compact module with small size? Thanks.
Okay. Yeah, that's a very good question, and actually it is related to our.
Who asked the question? I don't know who that is.
Oh, Professor Qingxia Li, my father.
Yeah.
Okay.
So.
Okay, go ahead.
Yeah. So this is a very good question, and actually it is related to our actual plan. You are absolutely correct that CPT, the use of CPT was meant to reduce the size of the apparatus. Otherwise, we can just use microwave fields to drive the transitions. And actually, the earliest atomic clocks are microwave atomic clocks. They do not use lasers to drive transitions. Yes, and for our experiment, yes, the design is very complicated, and right now we have not thought of a simple design for that, which indeed makes the use of CPT controversial, the significance of using CPT controversial.
Well, let me add it slightly differently. There's a question of what is fundamentally possible and fundamentally impossible, right?
Yes.
So in the early days, it was thought that, for a good Zeeman separation between the two zones
Yes.
in atomic beam-based microwave clock.
Yes.
When you make the microwave cavity, it was very difficult to keep the field exactly the same. And the CPT clock, it's just localized in one zone.
Yes.
And the smallest atomic clock that is currently available
Yes.
is actually CPT clock.
Yes, indeed. Yeah.
And you cannot make a similar one with microwave. So there is already existing evidence that the smallest clocks are made with CPT. Now, for the spin squeeze, you have to think about like the first computer, which fills the whole room. Now I have a computer in my hand that's 1,000 times more powerful than that. Okay.
Okay.
So miniaturization would take time, but there's nothing fundamentally prevents the spin squeeze CPT clock from being miniature.
Yes, and actually, due to the complexity, we have a backup plan to use the microwave fields for the transitions.
Right.
And and we have purchased the horn antenna for that purpose. So yeah, so if we cannot make the system for spin squeezing small enough, maybe use of microwave field is something we should do. Yeah. Oh, it's not charging. Okay. Yeah.
Okay.
Have I answered your question?
Okay. Thanks. That's interesting.
Okay.
Okay. So if there is no more question, we have to again repeat what we just went through at the beginning. But this time, don't leave. Please go outside, wait for a couple of minutes. We'll call you back in 1 or 2 minutes. Okay? That will to see you through the
Yeah.
And just can you mute the video and audio?